Welcome to lecture 17. We'll be covering the energy theorems and I'll be discussing the Betti's reciprocal theorem. So let's start with that discussion. And the Betti reciprocal theorem can be very advantageous. And let's go through that. The Maxwell Betti reciprocal theorem states that for linear elastic solids, the work done by the first system of forces one through the displacements caused by the second system of forces two equals the work done by the second system of forces two through the displacements caused by the first system of forces. And for this theorem to hold, it is necessary that we have a conservative deformation process. And the theorem here is important because it explains, this theorem explains why the stiffness matrix in 3D FEM finite elements is symmetric when we have a conservative deformation process and conservative loads. So anytime you have a conservative deformation process and conservative loads, you will expect a stiffness matrix in 3D finite elements that will be symmetric. And the Maxwell Betti reciprocal theorem basically is the reasoning behind that. So what is a Maxwell Betti's reciprocal theorem? I wrote it here. It states that for linear elastic solids, the work done by the first system of forces 1 through the displacements caused by the second system of forces 2 equals the work done by the second system of forces 2 through the displacements caused by the first system of forces. And so I want to walk you through what this is through an example. Let me try to explain what this theorem is really saying. I'll consider first a clamp beam. And this is my first system. In this first system, I'll define points 1 and 2. And I'll apply a load P here. And this load P is going to cause a deflection of that beam. And I'm going to call this deflection delta. Okay, this deflection, I'll call it delta. And that deflection is the deflection caused by this load P. This right here, I'm going to say that deflection delta was caused by load P. So I'll put delta sub P at point 2, so it's clear what's going on. And then I'll consider another system. But this time I'm going to apply the load at, I'm going to mark the same points, 1 and 2. This time I'm going to apply a load Q here at the same location where point 2 was. So that same location. So these beams are the same. And now this beam is going to deflect like that. And I'm going to call this deflection delta Q1. What Maxwell Betti Reciprocal Theorem is really stating is if this is a linear elastic solid, that the work done by the first system of forces, 1, through the deflections caused by the second system of forces, 2, equals the work done by the second system of forces through the deflections caused by the first system of forces, 1. In other words, P, so if I multiply P times this deflection here, that's going to be equal to the force Q times the deflection at this point 2. That's it. That's what it's saying. So let's consider the following example. I have a load P equal 4 pounds. And the deflection at this point, at a particular point, is measured to be 0.01 inches. Then I have another system. And in this system, I apply a load of 10 pounds. I want to know how much this deflects. And I'll call this X, that deflection. So the answer is very simple. What Betti reciprocal theorem is telling us is if the material is elastic and I have a conservative deformation process, I must have this situation 4 times X equals 0.01 times 10. 4X equals 0.1. X equals 0.1 divided by 4. Very simple. And now I have found the deflection of that beam given this information. So that's what Betti reciprocal theorem is telling us. So let's see how to derive this. So Betti reciprocal theorem states that 1/2 triple integral omega sigma ij for the first system of forces moving through the strains in the second system is equal to 1/2 triple integral sigma ij to epsilon ij 1 d omega. And I'll call this W, the work done. And I can multiply all the sides by 2 to get rid of that 1/2. And now what I want to do is now try to determine or demonstrate that this is correct, that this equation is fully correct. So the first step I want to do is substitute the fact that sigma ij equalsCijkl epsilon KL. And if I did that, I get triple integral omegaCijkl. And now I have epsilon KL 1 epsilon ij 2 d omega. Okay. And then we also have the situation that I can interchange indices. I can interchange indices because I have a conservative deformation process. So for a conservative, we know already thatCijkl has to be equal to CKL ij. We know that for a fact. And so for that reason, I can write that this is equal by interchanging indices to C KLij epsilon ij1 epsilon KL2. And I can do that by just interchanging indices. Okay. But this is equal to C ijkl again. And for a conservative deformation process. Okay, so therefore, we were able to show, we can show then that the expression I have here is correct because this is sigma ij for one, and this right here is this times that is, sorry about that, is sigma ij of 2 epsilon ij of 1. So I've demonstrated, I've proven this relationship right there. So that's how we start the demonstration. So step 0, I'm starting from here. And I'm going to start from this. So I'm able to prove step 0 by going through step 1. And this played a big role. The conservative deformation process played a big role in this derivation. We also know from the fact that we've gone through this many times that sigma ij epsilon ij is equal to sigma ij epsilon ij plus sigma ij omega ij, because this is 0. Because if I have a symmetric tensor times a skew symmetric tensor, that's equal to 0. We've demonstrated that in previous lectures. But I also know that sigma ij of epsilon ij plus omega ij is simply equal to sigma ij ui comma j. We've demonstrated that as well. So as a consequence, we can write the following, okay? I'm going to do a little trick right now. So I'll take this information and I'll plug it in here. Okay, let's plug it in there. So let's start with the left hand side. So I have triple integral omega sigma ij as it moves through 1 epsilon ij as it moves through. And we already said how this is equal to the triple integral omega sigma ij 1, and now I have ui comma j 2 d omega. And I'm going to turn that into, I'm going to do a little trick. I'm going to say this is equal to triple integral omega, and I'm going to do this derivative this way. And I'm going to put that comma j outside of the of this. like that. But obviously, this is minus sigma ij, comma j of 1 ui 2 d omega. You can see here that if I operate on this, this is equal to that. If I operate this comma j over this product rule, minus that, I get that. So it's a little trick, but it works, as you can see. And it's correct. There's nothing wrong in what I've written. It's mathematically correct. And so we can solve for the last term. Um, and you can see clearly that this is equal to that when I transfer the comma j to each of these terms in a product rule sense. Now, we all know from equilibrium, so this is step 3, step 4, use the equilibrium equations. And if I use the equilibrium equations, we know that sigma ij, comma j plus bi is equal to 0. And since I'm looking at 1, then I can now say that sigma ij, comma j of 1 equals the minus bi 1. So I can plug that in here, in that expression there. Okay, I can plug it in there. And I'll do that now. So I get the triple integral omega sigma ij of 1 ui 2 comma j plus now plus bi of 1 ui of 2. So a little trick here that we're performing. D omega. And now I'm going to use the divergence theorem, okay, on this term. Let's use the divergence theorem on that term. So that means integrate by parts. So integration by parts means that I'll put a 1 here, sigma j 1 ui 2 here, and then I'll have 1 comma j here, and I'll have sigma ij 1 ui 2, and now I transfer it here, nj plus minus, so now this is 0, and so nothing happens there, so now I only get a surface integral, double integral over the surface, sigma ij of 1 nj ui 2 ds plus triple integral bi of 1 ui of 2. And you can see here how I can use Cauchy's relationship, and this is exactly ti of 1. So therefore, I'm able to demonstrate that summary, I'm able to demonstrate that the triple integral of omega sigma ij of 1 epsilon ij of 2 is equal, or sorry, d omega is equal to double integral of s ti of 1 ui of 2 ds plus triple integral bi of 1 ui of 2. So I'm able to demonstrate that. But as you saw before, Betti's reciprocal theorem allows me to switch indices like this from sigma ij to epsilon ij and vice versa. So therefore, I can just interchange indices 1 and 2, and I basically get, as a consequence, that the double integral of ti of 1, ui of 2, ds plus triple integral omega bi of 1, ui of 2, ds, or d volume, sorry, equals, and now is equal to ti2 ui1 ds plus triple integral over omega bi2 ui1 d volume. Okay, so I've demonstrated Betti's reciprocal theorem, which is allowing us to calculate um, the forces in a second system or deflections in a second system. So let's say I have an example again, another example. I have the system that's fixed here. I apply a load here, P, and I measure a deflection. So let's say this deflects an amount delta 1 at point A. Okay, now I have the same system I'm looking at. And at this point A, I apply a load Q. And it deflects here at point B an amount delta B. And this is delta A. What Maxwell reciprocal theorem is allowing us to do is to take P times delta B equals Q times delta A. A very powerful idea that can be used in a lot of different situations. Let's consider now this example. And these are supposed to be squares, but I'm kind of rushing this through, so I apologize. And so let's say I want to measure the deflection of point A. So I say this point A and this point B. And I apply a unit load at point B. Unit load. And I measure this deflection. And the deflection is delta A due to a load applied at load P. So the deflection at point A due to a load applied at point B. And in the second situation, it's the same truss system, but it's going to look different because I'm not drawing it perfectly, but you get the idea. Yeah, I apologize for if things are not very clear in the diagram, but it's the same truss system, and now I apply a unit load here. And now here I measure the deflection, how much it moves. That's a deflection at point B due to a load applied at point A. Guess what? If I use Betti's reciprocal theorem, this tells me that delta AB times 1, so this times that, is equal to delta to 1 times delta BA. In other words, the deflections are equal, which is quite amazing to see that happening here. And that concludes example 2. I think we can do a lot more examples, and all of them will keep showing that this works. So we'll stop at this point and we'll continue the coverage of energy theory.